Hello and welcome back to CS10, Advanced Data Structures and Algorithms of the Department of Computer Science, UP Diliman. This video will discuss about analysis of non-recursive algorithms. At the end of the lecture, you will be able to understand the basic definition of time efficiency. We will review the three basic asymptotic notations used to represent the time efficiency. We will present one method for comparing the growth of two functions using limits, and finally, a general framework how to analyze non-recursive algorithms. Recall that we have several steps for designing an algorithm. So after proving that your algorithm is correct, then we can proceed to analysis of our algorithm. So there are two types for analysis. The first one is a theoretical analysis, and the second one is empirical. So for theoretical analysis, we just need to have the design of the algorithm or the actual pseudocode. For empirical analysis, needed na it is in code form or runnable program. So we will focus mainly on the time efficiency of the algorithm. But what exactly is time efficiency? Time efficiency is analyzed by determining the number of repetitions, so count of the basic operation as a function of input size. So there are two key information that we need to identify before we can give the time efficiency of an algorithm: the basic operation and the input size. So for measuring the input size, one obvious observation is that all algorithms run longer on larger inputs. So for instance, sorting 1 million numbers versus 10 numbers. So the running time of an algorithm is actually dependent on the input parameter. For sorting, searching, and most problems dealing with lists, the input size is the size of the list. For evaluating a polynomial, the degree of the polynomial or the total number of terms, kahit na isa lang yung input. Some not so obvious cases, for example, for matrix multiplication, although dalawa naman yung matrix natin, ang input size is not 2, but the dimension of the matrix, for example, like n by n. N by n here is the total number of elements, that's n times n. Why not n? Because hindi naman lahat ng matrices ay square matrices. So, better if total number of elements in the matrix yung input size for this problem. For primality testing, although isa lang yung input, the input size of primality testing is not just one, but the parameter should capture how large is the number. So, the right input size for primality testing problem is the number or log of n, or the binary representation of that number, because this can encapsulate the possible number of divisions to make. Okay, so that's the first one, the input size. For the second information, we need to identify the basic operation of the algorithm. So for the basic operation, it's the operation that contributes the most towards the running time of the algorithm. Yung idea is identify the most important operation of the algorithm, or the most time-consuming operation in the algorithm's innermost loop if it's an iterative algorithm. So, for example, for sorting, basic operation is the key comparison. For most mathematical problems, it's either addition, subtraction, multiplication, or division. Okay, so now that we identify the input size and the basic operation, now we are ready to define the time efficiency. The time efficiency can be represented in this expression. The time efficiency is basically the number of repetitions as a function of input size. So it's a function na ang input is the size of the input, which is represented here by n. Basically, T of n is the running time. C of n is the number of times the basic operation is executed times sub op. Here, C sub op is execution time per basic operation. So here are some examples. For searching for key in a list of n items, the input size is the number of list items, so that is n. And the operation is key comparison. For multiplication of two matrices, the matrix dimension or the total number of elements is the input size, while the basic operation is multiplication of two numbers. For primality checking or checking if a given integer n is prime or not, the input size here is the number of digits in the binary representation, and the basic operation is division. And for a typical graph problem, the input size usually is the total number of vertices or edges, and then the basic operation is visiting a vertex or traversing an edge. Now that we know how to identify the input size and the basic operation of an algorithm, let's check the three possible values for our C of n. So again, C of n is the number of times the basic operation is executed, but this count can actually differ depending on the form of the input. May mga input na madali lang, so yung number of times the basic operation is executed is less, and may mga input na worst possible input, so ma-maximize yung value for this C of n. So again, we have three different cases. And we have the worst case, the best case, and the average case. We say it's the worst case analysis for the worst input. So yung count natin is the worst, meaning that's the maximum over input size of size n. It's the best if it's the minimum over input size of n, and the average is the number of times the basic operation will be executed on a typical. So hindi ito yung average between the worst and the best. Okay, so for the average case analysis, it is required that we compute for the expected number with respect to some probability distribution. So let's try to distinguish the three cases using this example. So search, yung sinusolve ng sequential search algorithm na to. And for the search problem, the input is the array with n elements, and we have k as the search key. So, simple lang yung algorithm. The algorithm will try to look for that k in this array by checking each of the indices from the starting index up to the last position. So this is what this part of the algorithm does. And the first part of analyzing this algorithm is to look for the input parameter and to identify the basic operation. For the input parameter, we have the size of the array. So we have n. And then the basic operation in this algorithm is actually the key comparison. So itong step na to. So we have three different possible C of n. Yung worst case, best case, and the average case. For the worst case analysis, using this algorithm, marami tayong key comparisons if k is nasa last position ng array. So, we will have to go through each element from the starting position until sa last. And ang mangyayari is magkakaroon tayo ng n comparisons. For the best case, which is yung pinakakaunting possible na comparison, if k is in the first position. Okay? For the average case, we have n plus 1 over 2, but this computation isn't because n yung worst case and we have 1 as the best case and then divided by 2, that's the average. Actually, the computation for n plus 1 over 2 is different for two cases, assuming that k is in A, and the other case is when we have k not in A. For the average case analysis of the sequential search algorithm, assuming that k is in A, the average number of key comparison is n plus 1 over 2. And the proof for showing this is as follows. Okay, so we let P be equal to the probability that K is in A. So since this is a probability, the value for P is from 0 to 1. And then on the contrary, if P is or K is not in A, we have 1 minus P. Okay, so the third item here is the probability that K is in the ith position. So, since we have n possible positions, we have P over n. So, pantay-pantay sila ng probability na pwedeng paglagyan ni K for all I. Okay? So, to compute for the number of basic operation, we compute for the expected value of the number of the basic operation calls. So, for all possible cases, we multiply that for the corresponding number of basic operation calls. So, if it's in the first position, isa lang yung basic operation call. If it's in the second position, we need two comparisons. If it's in the third, we have three and so on. So that's I times the probability that it's in that position. And this is the case wherein we have n comparisons nasa last position. Okay? And if wala siya um, sa K, we have this. So we have n comparisons pa rin for the probability that K is not in A. So if we try to simplify this expression, we can get a simpler expression equivalent to this. So if K is in A, then the probability is 1. So we just simply substitute 1 here for P, and by careful evaluation, we can get this number. On the contrary, if we have P equal to 0 or K is not in A, if we let P equal to 0, then we have this. So, magiging 0 yung evaluation dito. And then we have N times 1 minus yung value ng P, which is 0, which is equal to N. So, tama naman. We have N comparisons if K is not in A. Okay, so the time efficiency can be represented exactly. So, as in exact computation ng number of times the basic operation is executed, or approximately. Kasi hindi naman necessarily laging exact yung running time complexity of the algorithm. So sometimes we can use asymptotic notations to approximately describe yung running time ng algorithm. So when we say approximately, we are using some functions, g of n, to describe our actual running time na, let's say, f of n. So to aid in our understanding, we can actually define these three notations as a class of functions. So it's in O of g of n. If your function grows no faster than g of n, theta, we can think of this as a class of functions that grows the same rate as g of n, and omega is the class of functions na f of n that grows at least as fast as g of n. So we can think of this notations as sets or class of functions. So sometimes it's we can see the expression na f of n is in O of g of n, or f of n is in theta of g of n. So to help us, there's a visual representation here of the relationship of t of n with respect to g of n. So we can say that t of n is in O of g of n if nasa baba siya nung function, or t of n is bounded above by some g of n. So, masasabi natin na t of n grow no faster than g of n. Okay, so all of the functions below g of n is in O of g of n. So, for example, g of n is n squared. Yung mga linear time, log n, yung mga mas mababang function is in O of g of n. So, yung contrary naman is if we have omega of g of n. So, that includes all functions above g of n. So, nandito sa part na to. Okay? We can say that t of n is bounded below by some function g of n. Or t of n grow at least as fast as g of n. Yan. So, using the definition of O of g of n and omega of g of n, we can say that the theta function is a class of function that grow at the same rate as g of n because it is bounded above and below by g of n. Ibigyan tayo ng better approximation if we have theta of g of n compared to loser description of the running time of the algorithm. Kasi dito, ang pwede nating ma-conclude is that, I have an algorithm and the running time of that algorithm is below this function. Parang ganun. Tapos, if we have this function, hindi siya bababa than this function. So, medyo loose yung representation kasi everything above this g of n is your possible running time. But if we have a theta of g of n representation of the running time, kaya mo siyang mabound in a smaller, yung mga functions lang inside nung g of n. So, bounded above and below. Mas kaunti or mas exact yung representation mo nung running time. So this is the formal definition of O notation, omega, and theta notation. I have some few examples here. So 10n is in O of n squared. It is because there exists some positive constant c and some non-negative integer n sub 0 such that we can claim this inequality. So, to prove that a certain function is in O of some function g of n, we just need to identify a c, parang existence ng c, and existence ng some n sub 0 such that we can prove that this is true. We also have an example kapag we have 5n plus 20 as our function, it is in O of n. So as an example, we have f of n equal to n squared plus n and g of n equal to n cubed. For n greater than equal to 1, n cubed is always greater than or equal to n. And same is true with n cubed greater than equal to n squared. So we can simply replace n squared and n by this expression. So since this is greater than equal to n squared and this is greater than equal to n, then if we can simplify this, we have 2n cubed. So makaka-establish tayo ng something of the form n squared plus n, which is equivalent to our f of n, and n cubed times some constant. Ang constant natin dito is 2 for all n greater than equal to 1, which is yung in-specify natin kanina. Thus, we have shown that this holds with n sub 0 equal to 1 and c equal to 2. And for the omega notation, we also need to identify some n sub 0, some c, such that this holds. So example is n cubed is in omega of n squared. So higher order polynomial is in omega of a lower order polynomial. So ganun din sa case na to. Okay. So as an example, we have f of n equal to n cubed plus 4n squared and gn equal to n squared. So for n greater than equal to 0, this can be established. So, pag nagdagdag tayo ng 4n squared sa n cubed plus 4n squared is always greater than this number. So for n greater than equal to 1, yung higher order polynomial n cube is greater than or equal to n squared. Okay, so for n greater than equal to 1, we can establish this. Actually, by transitivity, we can say that n squared is less than equal to this expression. So this is our original g of n, and this is our f of n. And this is true if we have c equal to 1, and that is true for all n greater than 1. So notice here that we use n greater than equal to 1, although we have an inequality dito na n greater than equal to 0. Well, if you get the intersection of the two, you'll get n greater than equal to 1. So for both cases, this is true, so kaya yun yung ginamit nating n sub 0. So for theta notation, it's easier because we can just simply use the definition of omega and O of g of n. Kasi to show that t of n is in theta of g of n, you just need to show that t of n is in omega of g of n and t of n is in O of g of n. So instead of identifying two variables na c and n sub 0. In this case, you need to identify some c sub 1 and c sub 2. And then a common n sub 0 such that this holds. So if we have f of n equal to n squared plus 5n plus 7, and we have g of n equal to n squared, we can establish the upper bound by replacing this with 5n squared and this with 7n squared, so that we can just simply take the summation of the coefficients and we can identify some c. So in this case, we have c equal to 13 to establish the upper bound for n greater than equal to 1. For the lower bound, medyo mas simple siya because n squared plus something else is always greater than equal to n squared for n greater than or equal to 0. So in this theta example, we identified n sub 0 equal to 1 because siya yung common na lower bound for the two inequalities. And we have c1 equal to 1 and c2 equal to 13 for the upper bound. Here are some strategies for proving the omega and the theta notation. For the omega, medyo mas tricky daw compared to the O notation. Quite often, we can pick some c na less than 1, and then we can just identify some n sub 0 that will work and that can prove the required inequality or condition. For the theta notation, we can establish this. Okay? So, hindi required na you have a common n sub 0, but we can prove that f of n is in theta of g of n if f of n is in O of g of n and f of n is in omega of g of n. Since we have a set representation for this, this, and this, then we can imagine that these are just set of functions, another set of functions, and yung commonality nila will be the set of functions in theta of g of n. Here are some important asymptotic notation properties. We have the transitivity. That is true for some f of n, g of n, and h of n. So, totoo siya for theta, O, and omega. For reflexivity, true din siya for the three different notations. And for symmetry, totoo lang siya for theta notation, not for O and omega. For transpose symmetry, magkabaliktaran si O notation and si omega notation. So, medyo mas mabilis mag-gets to because of the visual representation a while ago. Bounded above, tapos bounded below yung isa. And some important properties that involves logarithms and the rule of sums. Let's give some example for the rule of sums. So suppose we have g sub 1 and g sub 2 as the total running time of your algorithm. Sometimes it is important because suppose you have an algorithm with step 1 na equivalent dito, and then you have step 2 that have this running time. So since this is in O of n squared, this is in O of log n, ang total running time ng algorithm mo that involves step 1 and step 2 is the max between the two asymptotic notation. In this case, we have n squared. So we can simplify that the runtime for algorithm is O of n squared. Sometimes it's important to just compare the two functions. Say we have f of n and some g of n, and identify which one is higher compared to the other. So we can use the so-called limit rule to compute for identifying the case from the three possible cases. So if we have f of n and some g of n, we can simply evaluate this limit. And if the limit as n approaches infinity is equivalent to some L na equal to 0, this implies that this function is greater than compared to f of n. And if we say greater than f of n, we can establish that this function is in O of g of n or bounded above by g of n. Yung kabaligtaran nito is when we have an evaluation equivalent to infinity. Pag infinity naman, then we can establish that f of n is greater than g of n, and so f is in omega of g of n. So that's the two cases, and if it evaluates to a certain L na equivalent to some constant value, then f is in theta of g. So yeah, so that's it for the limit rule. And to compute for this, we can use some properties na kalimutan na natin from calculus. So we can simply recall the different properties that we can use for computing the derivative of certain functions. Let's have some examples na lang to illustrate how we can use the limit rule to compare the two functions, f of n and g of n. Suppose we have f of n equal to this, and we have g of n equal to n squared. We can simply evaluate the limit just by simplifying this expression. So first, we remove the constant. So yung 1/2 nandito na. We can simplify the f of n over g of n. This one evaluates to this one easily. So that's 1 minus 1 over n. And evaluating the limit we have, n approaches infinity. This is equivalent to 1 minus 0. So 1/2 times 1 is equivalent to 1. So since the evaluation is a constant value, which is equivalent to 1/2, we can conclude from the limit rule that this is in theta of n squared. Another example is if we have log of n base 2 as our f of n, and we have square root of n as our g of n. So in this case, wala na tayong constant that we can remove from the equation. We can simplify this by computing the derivative of log of n and square root of n. So using the rules as showed a while ago, this is equivalent to log of e times 1 over n, and then this equates to this evaluation. We can further remove the constants na because may mga pwede na tayong ma-remove, and then we can further simplify this one to be equivalent to this one. So as n approaches infinity, this expression evaluates to 0. So something times 0 is 0. So we can say that log of n is in O of square root of n. And so finally, we're on to the last topic for lecture 2.1, and that is creating a general plan for analyzing non-recursive algorithms. The first thing we need to do is to decide on the parameter n that indicates the input size. And the next step is to identify the basic operation. Third step is to choose between the worst, average, and the best case. Most of the time, we will choose the worst C of n. And then later on is we have to set up summation. Summation for the total number of times the basic operation is executed. So this is your value for C of n. And then later on, we get the closed form of the summation by using some useful formulas. Okay? So let's have some example. The first example is computing the maximum element. So for this algorithm, it determines the value of the largest element in a given array. So for the first step, we need to identify our input size. Input size for this kinds of problem is the size of the array. So we have n. And then for the basic operation, if we look at the pseudocode, the basic operation here is the key comparison. So we have this step. So basically, we need to count the total number of times this is called. By using the limit for I, we can set up a summation for C of n. The C of n is equivalent to the sum of the number of times this is called from I equal to 1 up to n minus 1. So, yung summation natin is the sum of all calls for this operation, which is ang count ay 1, and then I ranging from 1 to n minus 1. So, if we count the total of, if we try to simplify this expression, this is just equal to n minus 1, or it is in theta of n comparisons. So based from the bounds of the for loops, we can set up a summation that can count the total number of key comparisons. The first for loop is for I equal to 0 to n minus 1, and the second for loop is for j equal to I plus 1 to n minus 1, and here we have the count of basic operation, which is once lang. Okay, so we need to compute for the closed form of this summation. We can evaluate the first summation muna and then later on yung second summation. So this is a simpler summation equivalent to what we used a while ago. So this is simply the upper limit minus the lower limit plus 1. So this is n minus 1 minus I plus 1 plus 1. So if we simplify this expression, it's just equal to n minus 1 minus I. This can be split into 2. For this, it's equivalent to 1 times n minus 1. So we can remove n minus 1 here and then put 1 inside. So this whole thing is equivalent to this, and then this is the closed form for this. Okay, so by following the rules for algebra na lang, we can obtain n minus 1 quantity times n over 2. This is approximately equal to 1 over 2 times n squared. That is in theta of n squared. Okay, so we have two more examples, one for matrix multiplication and another for counting binary digits. But basically, we will just use the steps na ginawa natin for example 1 and example 2. So, hayaan ko na kayo na i-compute yung closed form for this sample algorithms. So, As a summary for this lecture, what we did was we defined the input parameter and the basic operation. And then we introduced three different C of N's. It could be the best, the worst, and the average case. And then we also reviewed the different asymptotic notations and defined it according to two possible definitions. One is the formal definition, that is, we need to identify some constant and some n sub 0 such that a certain condition holds. And the other type of interpretation is with respect to a class of function. So we defined omega of g of n as a class of function, O of g of n, and theta of g of n. And then next, we shared some properties of asymptotic notations. This is important, especially if we will manipulate expressions with asymptotic notations. We also introduced the limit rule, which can be used to compare the order of growth of two functions, f of n and g of n. So basically, we need to review the properties and properties needed to compute for the derivative of different functions, so that we can compute if one function is larger compared to the other or grows faster compared to the other. And then lastly, 6 na ba to? A general plan for getting the time complexity of non-recursive algorithms. As a summary, we need to identify the input parameter, the basic operation. We need to choose between the best, worst, and average case. And then set up a summation with respect to the basic operation used. And then compute for the closed forms. I also shared some useful formulas for computing the closed form of some summation. So it's just a matter of evaluating or simplifying some algebraic expressions. So that's it. That's it for the lecture 2.1. Next meeting or next video, we will discuss about analysis of recursive algorithms.